Hey guys, thanks for watching today, and today we're going to be talking about the concept of momentum. Now, you might have heard from physics that the equation for momentum is P equals mv, where P is momentum, m is mass, so that's measured in kilograms, v is velocity, that's measured in meters per second. Together, this gives momentum a formula or n unit of Newton seconds or kilograms meters per second, the negative first. Now, I'm going to go by Newton seconds for the rest of this video because it's a lot shorter. But now that we have the formula down for momentum, P equals mv, let's delve into what exactly momentum is. Now, to illustrate the concept of momentum, I'm going to give one of my favorite examples on the screen, and that is the case of a car. Let's say you are driving a car along the highway, and our car also ran into what's a little mosquito, represented by this little squiggly line right here. Now, let's say your car weighs about 100 kilos, and it has a velocity of 10 meters per second. That means it's going to have a momentum of 1,000 Newton seconds. Let's say this mosquito, on the other hand, weighs 0.01 kilos. And it's also traveling at a rate of 10 meters per second towards the car. So we have a car and a mosquito traveling towards each other. I want you to think about if the car and the mosquito collides, which often does happen on the road, which direction the car and mosquito would travel in. Well, in this case, the car and mosquito would travel in the direction of the car, according to our rules of momentum. Why is that? Well, let's look at the two momentums between the mosquito and the car. The mosquito has a momentum of 0.1 Newton seconds, and the car has a momentum of 1,000 Newton seconds. So since the momentum of the car is much greater than the mosquito, the car's momentum is ultimately going to cause the mosquito to move in the direction of the car. So I want you to think about, with this situation happening, how is that going to affect the velocity of the car? Because the momentum of the system is still conserved. In this case, it was 1,000 Newton seconds for the car, and then 0.1 Newton seconds for the mosquito. So because momentum is still conserved between the system, but the mass is also still there, and it's one system, the velocity has to decrease for the car to accommodate this, right? Because our mass is now actually 100.01 kilograms. That's how much we said, 100 plus 0.01 that the mosquito weighed. Our velocity has to be now less than 10 meter seconds to accommodate for this increase in mass. So mass increased in this case, m went up, and v had to decrease because momentum in the system, p, remained constant. So that would be the case of momentum in inelastic collision, where momentum is always conserved in any collision, but kinetic energy is not. We can go into the idea of momentum in an elastic collision. That would be the case of two pool balls, I guess they call them billiard balls, colliding. They would go back in opposite directions. But it's the same idea, right? I guess the only difference is that kinetic energy, which is equal to 1/2 mv squared, is conserved. Momentum, in this case, would also be conserved because the main takeaway of this video is that momentum always is conserved in collisions. So remember that momentum is always conserved. The other half part that I want you to think about in momentum is that momentum in this case is actually a vector quantity. That's because you have mass, which is in kilograms, that doesn't have any direction, but velocity, which is in meters per second, which is a vector. So because velocity, v, is a vector, that makes the overall quantity of momentum also a vector. So yes, momentum has direction. So remember these few things. That momentum is always conserved in a collision. It's equal to the product of mass and velocity, and that it's also a vector. I hope you found this helpful for a brief overview of momentum, and keep tuned for more content.